first let us see the definition of harmonic function. Any function which has continuous second order partial derivatives and satisfies the Laplace equation is called harmonic function. So what do you mean by Laplace equation? Laplace equation is here dou square u by dou x square plus dou square u by dou y square is equal to 0 is called as Laplace equation, and this is a Laplace equation for the function u. So when we have dou square u by dou x square plus dou square u by dou y square is equal to 0, whenever the function u satisfies this equation, that is a Laplace equation, we can say that u is the harmonic function. So what is meant by Laplace equation is, this is a Laplace equation. Suppose u is a function, then we can write the Laplace equation for u as dou square u by dou x square plus dou square u by dou y square is equal to 0, and this equation is called as Laplace equation. So whenever the function u satisfies this equation, we can say that u is harmonic. Right, now moving to the properties of an analytic function. First property is the real and imaginary parts of an analytic function are harmonic function, assuming the second order partial derivatives are continuous. That is, here let us consider f of z is equal to u plus iv. That is, f of z is an analytic function where u and v are real and imaginary part of an analytic function. So here what we have to prove here is u and v are harmonic function, which means that we have to prove u and v satisfies the Laplace equation. So first let us check whether u satisfies the Laplace equation or not. Since this is being an analytic function, here it satisfies the Cauchy-Riemann equation, that is CR equation. What is Cauchy-Riemann equation is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So here these two equations we are having. So first let us differentiate this equation with respect to x partially. So both the sides, if we differentiate with respect to x partially, we will have dou square u by dou x square, which is equal to, here it becomes dou square v by dou x dou y. And this equation we have to differentiate partially with respect to y on both sides. So while doing like that, we have dou square u by dou y square is equal to minus dou square v by dou y dou x. So what happened here is, if you notice these two equations, this is equation number 1 and this is equation number 2. So if we add equation 1 and 2, if we add equation 1 and 2, that is 1 plus 2 gives you dou square u by dou x square plus dou square u by dou y square will be the left side, which is equal to right side will be 0, because dou square v by dou x dou y and dou square v by dou y dou x both are same, and moreover both are of opposite sign will give you 0, which means that u satisfies the Laplace equation, and hence we say that u is harmonic, which means that real part of the analytic function is harmonic. Similarly, we can prove the imaginary part v also harmonic, right? So if we prove both u is harmonic and v is harmonic, we can conclude that the real and imaginary part of an analytic function are harmonic function. So this is property number 1. Next is property number 2 is, let f of z is equal to u plus iv be an analytic function, then v is harmonic conjugate of u if and only if u is harmonic conjugate of minus v. That is, here as usual we can take the usual notation, f of z is equal to u plus iv. So if f of z is equal to u plus iv, so here we can say that v is the harmonic conjugate of u. That is, imaginary part is the harmonic conjugate of the real part. So since f of z is analytic, this is analytic, we can conclude that I f of z, that is multiply both the sides by I. So I f of z will be iu minus v, that is I into I becomes I square. I square is equal to minus 1. So that iu minus v, this is also analytic, right? So that here what we can say that whenever this is analytic, always the imaginary part is the harmonic conjugate of the real part. So here based on what condition here we are taking, here this gives you V is harmonic conjugate of U. Similarly, this is the given condition. What we are proving here is from this we can conclude that U is the harmonic conjugate of minus V, because here we are having minus V as the real part and U is the imaginary part. So this is the first part. Since it is if and only if condition, what we have to do here is first we are assuming V is harmonic conjugate of U. We have proved U is the harmonic conjugate of minus V. Another vice versa is we have to assume U is harmonic conjugate of minus V and we have to prove V is the harmonic conjugate of U. So this is the first part. Second is the converse part. So conversely, what we are assuming here is U is the harmonic conjugate of minus V, we have to assume, which means that we have to consider another function g of z, let it be minus V plus I into U. Then only we can say that U is the harmonic conjugate of minus V. So once this is analytic, if you multiply minus I on both the sides, this gives you I into V plus U, because minus I into I will give you minus I square becomes plus 1. So this one, again since this is analytic, this is also analytic. From this what we can conclude here is that is the imaginary part. Imaginary part is V. So V is the harmonic conjugate of U. So this is what we have to prove. The converse part is we have to assume U is harmonic conjugate of minus V and then we have to prove V is the harmonic conjugate of U. So both the parts we have proved. So from this we can conclude that V is the harmonic conjugate of U if and only if U is the harmonic conjugate of minus V.